This is a very short video on electrocardiograms, ECGs, sometimes known as EKGs. It's K because there's no C in German, so in Europe they often use EKG. So what the electrocardiogram is exactly what it sounds like. It is a recording of the electrical activity of the heart, and it looks at what's happening in the SA node, the AV node, the bundle of His, the bundle branches, and the Purkinje fibers, and basically it tracks the action potentials through the myocardium. When sodium crosses the membrane to allow the action potential, then that's an electrical event because a charged particle is moving. And so that current, that moving of charged particles, can be recorded, and so we end up with a tracing that has three distinct waves: the P wave, the QRS, and the T. What happens here is when the SA node starts to depolarize, when it reaches the action potential, because it's spontaneous pacemaker cells, it happens right about here. There's a few cells depolarize, and then through the gap junctions it spreads and it spreads and it spreads throughout the atrium until the maximum number of cells have depolarized, and then there's fewer and fewer and fewer to depolarize, and so this represents the depolarization, etc., etc. We'll look at them a little more closely. So if we look at this is the P wave. The P wave is atrial depolarization. It starts at the SA node and it spreads throughout the entire atria, and it causes atrial systole. Now the atrial systole follows very shortly behind the actual P wave itself. The P wave is not the contraction of the myocardium, but the depolarization of the myocardium that results in contraction. So once the entire atrium is depolarized, the AV node has a small delay before it depolarizes, and so this ends up as the space between the P and the Q of the QRS complex. This is the time when the atrium is actually in systole, atrial systole, pushing blood into the ventricles. Then what happens is the sodium-potassium pumps repolarize the atrium, which would be deflecting of the ECG, but it's hidden in the much stronger depolarization of the ventricles. So the depolarization of the ventricles starts with the AV node, then moves down the bundle of His, the bundle branches, and out to the Purkinje fibers, like is illustrated here. Because the myocardium has so many cells and there's so much sodium moving, the QRS is far larger than the P. There's just more electrical activity because of the number of cells. It's a much larger node on the graph. So once the entire ventricle has depolarized, then the ventricle goes into systole and contracts. We have the isovolumetric contraction followed by the ejection phase. And this happens between S and T because there's a slight time delay of the latent period after depolarization. Then what happens is you start to repolarize, and the repolarization of the ventricle is the T wave. This is the sodium all being pushed back out of the cells and resetting and ready to go for the next one. So T is finished when the ventricles have completely repolarized, and then we end up with a period before the next heartbeat called the quiescent period. It's the period where the heart is relaxed and there is no electrical activity going on. Now, depending on the heart rate, the quiescent period is the time that changes. When your heart is beating quickly, the quiescent period is short. When the heart is beating slowly, the quiescent period is long. The PQRST complex is the same length whether your heart is racing or beating slowly. So by measuring from peak to peak on the QRS, you can also look at the time and the heart rate. So we considered the beat to be from here to here, the PQRST, PQRST, and this little space right in between the two is the quiescent period.